Okay, so this is my first venture into making our own videos for our learning at home, so bear with me. I'm sure that they will become more sophisticated as we go, but right now I'm still trying to figure some of this stuff out. So we are looking at Unit 3, Lesson 5, the inverse of a quadratic function. I've included our learning goals, success criteria, and practice that are all posted on the hub. But for the lesson's sake, our learning goals are that the inverse of the original function undoes what the original function has done. It can be used to determine which values of the original dependent variable produce given values for the original independent variable. The inverse of a quadratic function is not a function. We must restrict the domain of f at x for the inverse to be a function. Our success criteria is to determine the inverse of quadratic functions, and your practice is from Chapter 3.3, numbers 2 to 12. All examples for this lesson will also come from Chapter 3.3. Example 1. A. Graph the inverse relation. B. State the domain and range of f at x is equal to x squared, and the inverse of the relation. C. Determine whether the inverse of f at x equals x squared is also a function. Give a reason for your answer. So we start out with the example showing us a graph of f at x equals x squared. Now, we know that we're dealing with a parabola here, and we need to construct a graph of the inverse. Now, the textbook has you just create a graph using the inversion of points. So for that, we would take a table of values for x and y, and we all know the key points of this parabola. We go from -2 all the way to +2, and for y, we would see values of 4, 1, 0, 1, and 4, because we are squaring each of the values of x. So now that we have our points, we recognize that the inverse is a relocation of x and y. The values that were x become y, and the values that were y become x, meaning we are going to see our new x and our new y given that all the values of x were what once were y. So 4, 1, 0, 1, and 4, as well as -2, -1, 0, 1, and 2. Now, in the text, it shows us our graph here, where we have the function f at x equal to x squared, and we see the inverse of our function, which is plus or minus the root of x. They've demonstrated that the two arms of our inverse would be the positive root of x and the negative root of x, and they've assigned them different colors just to help you identify that. Now, one question that I've been getting a few times is how did we arrive at the actual equation for the inverse of f at x? And this textbook kind of glosses over that, unfortunately, in this example, but we've already learned how to take the inverse, so we would just have to actually go about determining the inverse of this equation. So if we wanted to determine the inverse of the equation, we would start out by writing that f at x is equal to x squared. And if we wanted to find how our inverse would be determined, we would take y equals x squared. We would relocate them, so x is equal to y squared, and then we would solve for y. So to do that, we would take the square root of both, which would give us plus or minus the root of x is equal to y. There we have the equation to our inverse. So to finish this off, we would say that the inverse of f at x is equal to plus or minus the root of x. remembering that the plus or minus piece is critical because that's what gives us our arms that open upward and downward in the root function. Question B asks for us to state the domain and range of f at x is equal to x squared and the inverse of the relation. So we know that we can use the equation or the graph to get our domain and our range. In the case of our function f at x, our domain is just going to be x is an element of the real number system. That will be true for all parabolas unless we put some kind of restriction or condition upon them. And the reason this is true is that we will be able to increase and decrease the value of x and still get an answer for every single function that is a quadratic relation. Our range will face some conditions. We have a line connecting our points, so we still would put y as an element of the real number system, but we have a minimum point on this parabola. In this case, the vertex is located at 0, 0, so the lowest point is 0. Y must be greater than or equal to 0. For our inverse, we know that the domain and range will just be a relocation of the domain of f at x as the range of the inverse, and the range of f at x as the domain of the inverse. We can also confirm this from the graph. So our domain is going to be that x can be any real number with the condition that x is going to be greater than or equal to 0. Similarly, for our range, we look at the domain of the original, so our range will be that y can be any real number. And we can see that in our graph, okay? We notice that we have the vertex at 0, 0 again, and that we can increase and that we can decrease, and that we will always travel from 0 onwards in the positive domain. This means that our condition is that x has to be 0 or greater, and we can see that y has no condition because y can forever increase and y can forever decrease. Part C asks us to determine whether the inverse of f at x equals x squared is also a function, and we need to give a reason. So there are a couple ways that we can answer this. We have a graph, so that means that we can use the vertical line test, meaning we just drop a vertical line, and we see that the equation of plus or minus root x would cause us to have 2 points of intersection with the vertical line. Therefore, no, the inverse of f at x is not a function. And the reason for it is that it is a one-to-many relationship. Thinking back to Unit 1. Okay? Now we could also arrive at that conclusion from the equation. And the only clue that we need to arrive at that from the equation is that the inverse of f at x is equal to plus or minus the root of x. And because of this plus or minus, it tells us that it's also going to be one-to-many. All right, and the reason it's one-to-many is because we have an arm of a root function that opens upward, the plus, and an arm of the root function that opens downward, the minus. I wanted to just take a moment and discuss some form issues that we've been using. So we've been talking about the inverse of f at x, and we said that in the previous example we had plus or minus the root of x. But we also identified that because of the plus or minus, this is not a function. That means that we shouldn't actually be saying that the inverse of f at x is plus or minus the root of x. And as we'll see as we move forward, we stick to using y when we're dealing with plus or minus the root of x, and then we place conditions upon x in order to make the inverse a function. We'll detail this in example 2. In example 2, we are given the quadratic function f at x is equal to 2 times x plus 3 squared minus 4. We're asked to graph the function and its inverse, as well as determine the equation of the inverse. Well, we're going to do b before a, just because I think it's more important that we work through taking the inverse, and you're welcome to use Desmos in order to graph the two. But if we know that f at x equals 2 times x plus 3 squared minus 4, we'll start by relocating and saying that x is equal to 2 times y plus 3 squared minus 4. And we need to start trying to isolate. So to isolate, we're going to add 4 to both sides, giving us x plus 4 is equal to 2 times y plus 3 squared. We'll then divide both sides by 2. And now we're dealing with x plus 4 over 2 is equal to y plus 3 all squared. Our next step would be to take the root of both in order to cancel out the squaring. Remembering that when we take the root here, we have to make sure that we are identifying that this is plus or minus. So running out of space there, I've had to erase and slide that on up. But continuing along, we now see that plus or minus the root of x plus 4 over 2 would be equal to y plus 3. So we're almost done. We're going to subtract 3 from both, which will leave us with negative 3 plus or minus the root of x plus 4 over 2 is equal to y. Just fixing that plus there. And so like I mentioned before we started this example, we've got plus and minus, meaning that we have two arms to a root function or something that will look something along the lines of that, right? A plus arm and a minus armor. We can't say that that's a function because it fails the vertical line test and therefore is not a function. So instead, we're going to need to place conditions that will allow us to have an actual function. Before we try and make any decisions on how we need to restrict x, we should look at what the graphs would give us. Now, I'm going to recommend that whenever you're asked to graph, you use Desmos, but we're going to do quick sketches here as well. So here's our Cartesian plane, and we look at f at x up here. We have f at x equals 2 times x plus 3 squared minus 4, which means that we're going to find a vertex at negative 3 and negative 4, and we're going to head upward stretched by a factor of 2. Again, you really should use Desmos to get an accurate depiction of this, but I'm just doing a quick sketch. Now, we've already taken the inverse, so we know the equation, and we also know that the points on the inverse are a relocation of x and y. So if our original vertex was negative 3 and negative 4, that means that the new vertex for the inverse will be at negative 4 and negative 3, and give us something like that. The reason we're going through this right now, before we actually finish off the equation, is that we can see that if we were to get rid of the arm that grows as x gets more negative, we would also get rid of the arm that will grow downward for the inverse. In other words, if we restrict x at its vertex for f at x, then the inverse of f at x will now be a function. And so, in light of this, we can say restrict x as greater than -3 for f at x. And from there, we can say that the inverse of f at x can be found from the equation of -3 plus the root of x plus 4 divided by 2. I'm not going to bother to simplify that to x over 2 plus 2. I think that leaving it as a fraction in this case is fine.